Brian Harrel, Greg Meador, Robert Valentino, and Kashyap Yellai present Inertial Confinement Fusion. In 1905, Albert Einstein presented his special theory of relativity, along with his now famous equation E equals mc squared. This equation states that the amount of energy stored in matter is equal to the mass of that matter times the speed of light squared. Unlocking the energy trapped in matter by converting it directly to energy is the holy grail of power production. The way to release all of this energy is through fusion. Fusion occurs when a deuterium and tritium molecule are forced together under intense heat and pressure. These two molecules fuse, forming a helium molecule with the emission of a single neutron, which releases a gigantic amount of energy. Unlike thermonuclear fission used in nuclear power plants, fusion would be environmentally friendly and produce no combustion products nor greenhouse gases. The products of the fusion reaction, helium and a neutron, are not radioactive. With proper design, a fusion power plant would be passively safe and would produce no long-lived radioactive waste. If you're anything like me, it's a little bit difficult to imagine what 186,000 miles per second times some matter actually comes out to be. But when you look at it as follows, it'll make a lot more sense. When fusion's taken into account and the amount of deuterium in a cup of water is calculated, it comes out to be the equivalent energy that is contained in 19 gallons of gasoline. Though the concept of fusion is not new, the sun's been doing it for billions of years. Actually getting the energy out of it on Earth has been much more challenging. Physicists at Lawrence Livermore National Laboratory in Livermore, California, are going to change all of that. Work has now been completed on a massive project called the National Ignition Facility, or NIF. NIF is expected to demonstrate fusion ignition, the release of more energy via fusion burn than the energy used to initiate it. Let's take a look at how this is done.
Far beneath these clouds lies the National Ignition Facility, located at Lawrence Livermore National Laboratory in Livermore, California. This facility has been built to bring star power to Earth. It is the world's largest and highest energy laser system. Containing 192 laser beams, NIF will explore controlled nuclear fusion to ensure global security, enable sustainable clean energy, and advance our understanding of the universe. Here you see the 8 beams split into 2 groups of 4 beams each, one group traveling up and the other traveling down, heading for equidistant entry ports on the target chamber. Finally, the beams pass through the final optics assemblies, which convert the original infrared laser light to ultraviolet. The beams then converge on the 10mm target assembly called a hole rod, generating a bath of X-rays. This causes the tiny target sphere to implode and ignite in a controlled, self-sustaining fusion reaction. The same process that powers the stars.
In the next few minutes, we will look into Inertial Confinement Fusion Process, or the ICF, as a power source and what are its economic and environmental implications. Let us start by looking into the future demand for power in the US. As can be seen in this plot, the power requirement in the coming years would grow exponentially, and generating power just by burning fossil fuels would not be sufficient anymore. Hence, we need to be looking into some alternative power resources. Nuclear energy as an alternative energy resource. Fossil fuel accounts for a majority of power generated across the world. Nuclear energy is the main alternative to burning fossil fuels to produce energy. Nuclear energy can be harnessed in 2 different ways. One is by nuclear fission, which is a conventional nuclear energy generation process, and the other one is by nuclear fusion, which is laser inertial confinement fusion process, which was explained previously. Now, let us take a look at the economic implications of ICF. ICF plant would have very high startup costs. However, in the long term, the estimated operational cost will be 40% less expensive than a coal plant of the same size. ICF reactor uses similar turbo machinery as coal. Hence, it will cost the same for setting up the combustion chambers as coal plant of similar wattage. ICF requires extraction of deuterium and processing it into usable pellets, which is expensive than processing and shipping coal. However, it is less expensive than the conventional nuclear power generation by fission process. Now, let us take a look at the environmental implications. Deuterium and tritium, which are used as fuels in ICF, are derived from water and is abundantly available. This provides energy security across the globe. Power generation does not emit any carbon-based products. Therefore, it is a clean alternative to power plants based on fossil fuels. Fusion process, unlike fission process, does not pose a danger of chain reaction. Hence, does not create a runaway meltdown and does not release long-lived radioactive nuclides. ICF fusion does not require any active cooling system to absorb immense residual heat. Therefore, ICF power plant would not pose a threat in case of natural disasters like tsunami in Japan, and decommissioning requires only the removal of steel and concrete structures. One can just walk away from the plant without any consequences.
The United States Department of Energy is funding NIF in its nuclear fusion research. When NIF has a technology to produce nuclear fusion as a source of energy, the U.S. will have a competitive advantage over every country in the world. This advantage comes from its resources, namely the technology in developing energy cheaper than any other place on the planet. Another source advantage comes from its capabilities, or the knowledge that it will be developing while it is producing the technology and future technologies which will follow. Does it create value? Nuclear fusion's value comes from producing unlimited amounts of electricity at a discount price compared to the rest of the world. Americans' living costs will drop dramatically, which means they'll have more to spend. Corporations will have lower variable costs, which will increase revenue and lower prices. When prices fall, sales and exports will increase. Even tax revenue will increase due to the increase of production and sales. Is it rare? No other technology in the world can compete with fusion. The U.S. will have the first-to-market advantage, which is also rare in itself. Is it easily imitated? Like nuclear fission, this technology can be imitated by other countries if they steal it or if we share it with them. However, the startup costs are incredibly high and the technical know-how will take many years to develop. Furthermore, the technology will continue to advance and other countries will be playing catch-up due to the U.S.'s learning curve advantage. Does the U.S. have the organization? The U.S. has the capabilities and resources to build the needed infrastructure and exploit this new technology. However, a technological breakthrough such as this would need to receive approval from Congress. Unfortunately, private corporations in the industry may attempt to lobby against fusion for their own survival. Furthermore, the question to privatize this technology or keep it federally controlled will be another controversial issue. Regardless, this technology will definitely change the way the world looks at energy. The source of energy itself will be sustainable, and if the U.S. does develop this before anyone else, they will only add to their competitive advantage in their resources and technology, and will continue to be a leader in this world.